Let's now look at the final unit of the module, which focuses on um, digital control systems. And on this final unit, we will look at the computer applications in digital control systems. We'll look at sample data systems, the use of the Z transform in analyzing these digital control systems, closed loop feedback systems, sample data systems, and performance of these sampled data systems. And computers are widely applied in control systems, and these digital computers can be in the form of microcontrollers or they could be in the form of PLCs regularly. This is the most common one, or FPGAs or any other type of digital computers. And digital computers are distinct from the physical world in the sense that whereas the physical world is full of analog signals, digital computer systems process digital signals, or what you call discrete time signals. By that we mean a discrete time signal is a signal that has been sampled at specific points of time or at a specific interval. So if you look at this figure, this could be an example of a temperature in a room. But after sampling, a discrete time signal would be a signal whereby the value of the signal is only known at discrete points, at 0, at 1, at 2, 3, 4, 5, and so on and so forth. So a digital computer becomes more comfortable it's designed to work in this domain with these types of signals, not the analog signals. So the control loop requires some form of signal processing in a form of sampling to discretize or to make this continuous analog signal into a discrete signal. Now, a typical computer control loop, or a control loop that involves a computer, which we shall, for the remainder of the course, call a digital control system, would look like what's shown in the setup. So you have a digital computer taking in reference input as well as the feedback signal, both of which are digital because a digital computer works with digital signals, and the computer also giving out a digital signal. And this digital signal has to be converted to an analog signal because most of the process and actuator would be operating using analog signals. So you can imagine here, for instance, the speed of the motor, which would be in the form of a digital signal spelled out by a computer in bits, and then the analog to digital converter will convert it into a relevant, say for instance, a voltage, a continuous voltage, which would be an analog signal. So a digital to analog converter would be a signal processor which converts from digital to analog. And then this would give this to an actuator, say in this instance a motor. The motor would then turn, maybe it's steering a tank, which is our process, to mix a certain blend of chemicals, and then the output would be, say, that particular, how well the blend is mixed. And then this process would then be measured by a sensor to give you potentially an analog signal, but this analog signal has to be converted from an analog to digital signal so that the computer can understand this information. So you see in this control loop, you have both analog processing modules, which are the actuator, the processor, and the sensor, and you need to have some form of signal processors here, which is the digital to analog converter, DAC, and the analog to digital converter, ADC. And you have a digital computer. All of these have to work together, and for this to work together, you need this signal processing. So the advantages of having computers within the control loop or digital control systems is improved sensitivity of measurement. So digital sensors can have high sensitivity, reduced sensitivity of signal noise. There could be some intelligent sensing of noise that or signal processing that would be able to eliminate noise, and flexibility as well, in the sense that the computer can be changed or easily changed. It is the capability to easily reconfigure a control algorithm in software. So your control algorithm, instead of being implemented by connecting circuits when like you do in an analog control system, that could just be written in a form of software code in software, which can be easily changed from time to time quickly enough without the needing of soldering or changing any other mechanism with hardware. So a sample data system, we call generally these systems whereby you have both digital and analog signal processing devices, sample data systems, because they work with both. This in order for the control loop to work, the digital computer has to sample your signals. So sample data, or so we refer to sample data as this discrete signals. So you have a analog signal, which is continuous signal coming in, and then a sampler, which is normally represented like a simple switch, is chopped up or sampled into a discrete signal like this, and then the computer algorithm will work on this discrete signal. So sample data is data that is obtained for system variable only at discrete intervals, which are denoted x of kt. So x of kt or x of k. So this would be the data in this case, this which will only define x of x0, x1, x2, x3, and so on and so forth. And what's important to note is that the sampling time can change. Sometimes you can sample it slower at a rate of 1 second, and sometimes you can sample it much faster at a rate of 2, at the rate of each and every half a second. And this will change actually the nature of the control system that you have, generally speaking. Sometimes you later see it can affect the stability of your whole control loop, how you change your sampling time. Now, so in this case, for instance, here you have a digital computer connected to an analog, or a digital to analog converter. So this would be turning that sampled data back into digital, into analog equivalent, and then the actuator and the process will take an analog input. That analog input is measured. When it's measured, it's going to be then converted back to digital. So this would act as a sampler. In this case, it will sample it to a digital form and then come back. So the signal is sampled in digital form and converted back into an analog form. So there's these two types of conversions here. So so approximating this analog signal to a digital signal, we sometimes use what's called a zero order hold system. A zero order hold system is a system whereby the analog signal itself is the output signal, which is like an analog signal. It's made up of these different steps, in the sense that you sample and hold the value up until you get the next sample. You sample another one, hold it up until the next sample. You sample another one, hold it. So it will be like a series of staircases. So this signal is the signal that approximates the analog signal that was initially coming into the computer. So you will find that this, in fact, the process or the plant itself doesn't see the analog input, a completely smooth analog input, but it sees this step or staircase type of system, type of signal, which has been created by a zero order hold system. So this type of signal introduces what's called quantization errors. So the quantization error, by that we mean that, say for instance, you have this R of t, it's a simple curve of an exponential waveform that falls down from 1 to 0, and then depending on how you sample it, the sample and hold output would have the approximation of this particular signal will be of this form, the steps p of t. And then if you use, say for example, a sampling time of 1 second, then you'll have this type of steps. If you use a sampling time of 0.2 seconds, you would have at least a smoother or a closer signal that's closer to R of t. So the error in which there's an error, or there's a difference between the R of t and its approximation, which is P of t. So there's always an error that this sample and hold process introduces, and this error depends on how quickly the sample has been. That is, the quantization error also depends on the sampling time as well. And so this sample and hold system, which is used in sample data systems, in most cases, it has a transfer function of this form: 1 over E minus S of t over S. So it has that transfer function. And it's important to take note of this transfer function, because each and every plant thereof going forward will have this as part of this transfer function, because the computer itself is communicating to the plant through this zero order hold system. Now, in order to analyze digital systems or digital control systems, we need a new type of transform. Instead of just using the Laplace transform, the most convenient transform is called the Z transform. If you're American, the Z transform. And the Z transform simply means the Z transform of a signal f of t. It represents the discrete time or digital representation of that signal in the Z domain. We'll call it the Z domain instead of the S domain, whereby Z is equal to e to the power S of t. This S is like that Laplace transform variable, the complex variable given by the Laplace transform. So you take the Z transform of f of t, normally represented as f of Z, which is basically an infinite series of the sample values f of kt, that is the sample values, with Z to the power minus k being the variable that varies from there. So Z to the power minus 0 would be the first sample, Z to the power minus 1 would be the second sample, Z to the power minus 2 would be the third sample, and so on and so forth. So if you have an impulse, for instance, unit impulse at time t is equal to kt, its Z transform will simply be Z minus k. If you have a unit step whose Laplace transform is 1 over S, the Z transform would be Z divided by Z minus 1. And then if you have a ramp, which is 1 over S squared, the Z transform of that will be T Z minus 1 squared. The T here would represent the sampling time. So the Z transform also depends on how fast you sample your signal, as initially anticipated, and so on the rest as well here. These are typical examples of the Z transform. So the Z transform, to recap, is important in analyzing digital control systems. Now, this is a typical example or setup of an open loop discrete time system. You have your input continuous time signal, which is sampled with a sample and hold system, and this particular sample and hold has a t of 1, which means it has a sampling period of 1, which means each and every second it will sample your incoming signal R of t, and then it will produce R star of t. This R star of t is then held or sampled and held to produce P of t. So P of t is an approximation of this final R of t going into the process. It goes into the process, and then the process therefore gives a Y of t, and then this P of t is going to be in the form of a steps. This R star of t is going to be discrete samples. This R of t is going to be an analog signal. This one is analog. This one is discrete time. This one is going to be in the form of steps. This one is which is also a form of analog, but it's steps. This will be in a smooth output. Let me just give a picture here. For instance, here you would have R of t here. You would have something like this, which is continuous, and then with R star of t, you would have something like this, which samples different instances. And then with P of t, you would have the same samples here that follow the R star of t, but this would be, you will sample, hold, and then go to the next sample, hold, go to the next sample, hold, and so on and so forth. So it would be like this is some form of analog signal, but in the form, it will have these steps like that, and then the Y of t on the other hand will be something which we expect an ordinary analog signal to be. So these are the type of signals that you are looking at here. And remember, we said this would be the transfer function of the sample and hold. And so the transfer function of the open loop, if you look at it from this perspective, it's going to be when you multiply the GP transfer function with the sample and hold transfer function, and then it gives you that. And you expand into partial fractions. This you have learned in control systems too. Then you can put this similar equation, it comes to that. And if we use the table 13.1, which was in the previous slides, to look at the Z transform, this would be the Z transform of 1 over Z minus 1 times Z transform of the whole of these partial fractions. And then that should give you, in this particular 1 over S, you will see that your Z transfer function comes to something like this. And this Z transfer function, what's important to note is that it has T. So whenever you discretize a plant, your sampling time is very important. T, the sampling time is part of it. It forms, so the Z transform will differ, even if the plant is the same, but the Z transform will differ based on what sampling time is used. So in this case, G of Z is going to be that. Now, if you use T is equal to 1, you will get this in particular. So this becomes the Z transform of the whole plant. Now, this can be done in a computer control system design tool, in this case in Octave that we used. We used the control package in Octave. So the control package in Octave, you load it here. This is our control system design tool. And then you give it the transfer function. Remember, this transfer function is like 1 over S squared plus S plus 0. Remember this, when you multiply S by S, you get S. When you multiply S by 1, you get S and then plus 0. So if you write that in full, it will give you this array. So the first what do you call here, the first one, the coefficients here of this polynomial is going to be, the first one is 1, second one is 1, the third one is 0. So you have 1, 1, 0. On top, the polynomial is just has a power of S is 0, which is 1. So the top polynomial here is that. So you say your transfer function with the numerator is 1, the denominator is 1, 1, 0. The sampling time is 1, and then you simply create your transfer function in this case. That becomes your transfer function. Now you discretize it. You say the transfer function of G of Z. So what you're doing, you're using the function called C to D. What the function does is it takes from continuous time or analog to discrete time or digital. So from continuous time to discrete time or to digital. So C of D, so you're taking that plant from, using the zero order hold, you're taking it from the continuous time GP of S to discrete time GZ using the sampling time of 1. And then this gives you this, which is approximately equal to that. You will see the approximation is not quite exact. There are some small mistakes that the that the design tool has. In particular, here you see this is 9, whereas that is 8, and then you here 4 4. You see this one is 2, this is 4, but very small inaccuracies in the calculation. But generally, that's how you create your Z. You calculate your Z transform or Z transfer function, and using this tool. Yeah. So it takes some time, practice these commands, and then see for different types of GP of S what transfer functions you can get. Go ahead, use your examples in the book and tutorial to see and practice these commands. Now the closed loop system, much similar to what we have dealt before in designing a feedback control system. So instead of just having the output there, we introduce this feedback line. And then if you introduce the feedback line, similarly, we know that then it means that the closed loop transfer function T of Z will be equal to that. Now, if that should be your closed loop transfer function, this is the same as any negative feedback system. If you have G of Z, you substitute that G of Z into here, and then you make the calculation, then your closed loop transfer function, let's call it T of Z, then becomes this. This can also be done in the control systems toolbox. Look in your reference text where they create an example of a closed loop feedback system. You should see this example, how you close this feedback. There's a single line that you can use just to close the feedback and get this transfer function. In fact, I think later on we'll talk about how this is done. Now the closed loop transfer function is that, which means now we can obtain, for instance, the system response from this closed loop transfer function. So the system response would be Y of Z given the input R of Z, and then the Z transfer function should be like the coefficients. The coefficients here would be Y of, okay, let me use the blue line here. This would be the first coefficient, the second sample, the third sample, the fourth sample, the fifth sample, and so on and so forth. So you will see you'll get the different K's here. 1, 2, 3, 4, 5. So this would be your Y here of K, the values. So this would be your, this could be the value of the samples here, and then Z minus K simply indicates the value of K. In fact, normally we start at 0. We start the sample with the initial one. So this would be 0, 1, 2, 3, and 4. So consider, for instance, if you are looking for a step response. If you're looking for a step response, we know that the step input, so we want to calculate Y of Z. Y of Z is going to be equal to the T of Z times R of Z, right? And we know already T of Z is this. We substitute that, and then if this is a unit step from the table, we know that the unit step will have this as your R of Z, and then you multiply these two, and then this should give you something like this. This should give you that. We have the Z at the bottom here and the Z minus 1 here, and then this belongs to the T of Z transfer function here. And then you can get this as your output Y of Z, but sometimes you don't want to get this output as Y of Z like that. You want to get it in this form. So if you want to get it in this form, what does this mean? This means that the first sample is going to be 0.36, so this one would be that 0.36. The second one would be 1. The fourth one would be, no, the third one would be a bit higher, 1.4. So it'd be something like higher there, 1.4. Another one would be also slightly higher at 1.4. The third one would be just like 1.1, and so on and so forth. So you can be able to see what the output looks like. So in a way, you can be able to foretell stuff like performance. What is the performance of the loop? In the sense that you can see if there's a peak overshoot, you can see this going up and then going down and damping down. If it becomes unstable, you can see the outputs going up and up and up and up and up, being unbounded. You can see, for instance, you can tell, for instance, that the system might be unbounded for a bounded input, which might mean that it's slightly unstable. So we'll talk about, in fact, this issue of stability a bit later on. But first, what we need to note is that in order for you to be able to assess the output, you need to be able to do this division. There's a division here. You need to be able to do you need to be able to tell what yk of t is. You need to be able to tell the zero sample, the first sample, the second sample, the third sample, and so on and so forth. And to do that, you go into the process of finding the Z transform inverse. And it's easy to find the Z transform inverse if you put it like this as an infinite series, because this would correspond to yk is equal to 0 to 1 to 2 to 3 to 4. And this can be done using long division, for instance. So as initially stated, if we want to recover the time domain samples of the function f of t, we can only recover this time domain samples at specific intervals, f k of t, and the sampling intervals. And this is called taking the inverse transform. So in fact, we want to find y of kt if we have y of z. So there are two ways of doing it. Long division is one of them. Partial methods of partial fraction is one of them. This is similar to that you do a similar process or procedure as the one you did for a Laplace inverse transfer function. So I would just like to talk about this first one, the long division method. So we'll just focus on this one for now. And then, so what we do here is take, for instance, we have the Laplace transfer function of the output signal. So the output signal is this 2z squared plus 2 divided by z squared plus 1.5 minus 0.5. And we want to recover the signal yk of t. What are the samples? Maybe the first 4 samples, for instance. Now, in this instance, what we do is we use the long division method. If you use the long division method, we will come up with an infinite series. So the first few values of the infinite series will be 2 minus 2, z to the power minus 1 plus 4, z to the power minus 2 minus 7, z to the power minus 3, and so on and so forth. So at this point, we are satisfied. We have samples 1, 2, 3, 4 samples. We have 0, 1, 2, 3. And then we know, based on this equation, that in fact this infinite series in this case is like this. You have a coefficient f of kt multiplied by a power of z, which is minus k. So you have here minus k is 0 here. Here k is 1, k is 2, k is 3, and so on and so forth. So your coefficients are 2, minus 2, 4, and 7 based on this calculation. You can see that. So which means then we can simply say the samples here, the 0th sample, y of k when k is equal to 0 is equal to 2, y of k when k is equal to 1 is equal to minus 2, and then you have a 4 and a negative 7. So that's how you can recover this sample. So in fact, we can plot then the second, we can use this to plot, say, our output. In this case, we can plot our output on some graph. So let's say we have 2, we have 4, we have 2, we have 4, minus, minus, and then we are plotting y of t this side, or maybe let's say kt, and then here we have 0, 1, 2, 3, 4, and then this is k, or kt. Sometimes just write k. So we can plot this sketch. We have the 0 sample here at 2. And then the sample at 1, which is negative 2. And then the sample at 4, sample at 2, which is 4, at 3 is -7. So we can plot something like this. So the way it will operate is, if you finish this graph, we will have that it becomes 1, and then you hold it up until the next sample, and then here you're going to hold it up until the next sample, and then that one you're going to hold it up until the next sample. So our graph will be like this. This is basically what you will get out of your assessment to find what y of kt is. So in another example, let's just use long division then to find y of kt. So we can do this calculation manually. Let me just do a calculation here. Hopefully everything will be clear. Right. So if you do long division, remember from grade 4, you learned that if you do long division, then put in the numerator here, and then the denominator here. And then we take note of what happens. So we take z, we go z squared into 2z squared. That gives you 2. It gives you 2. You say 2 multiplied by, z squared. You get 2z squared. 2 multiplied by negative 1.5 z, you get minus 1.5 z, and sorry, not minus 1.5. 2 times 1.5 is 3. This is 3z, and then 2 times 0.5 is 1 plus 1. Right. Then you subtract the whole thing, you get positive 4z, and then minus 1. Then you go 0 into 4z, that would give you 4 times z to the power minus 1, because then you multiply that out, you get 4z, and then you have minus 6z, but the z is to the power 0 in this case, because remember this is minus 1 and z, which is basically a 6, and then plus 2 in this case, because it's 4 times 0.5 is 2, z to the power minus 1. And then you subtract that, that gives you, because you get a 0 here, you get a minus 1 minus 6, it's 5. Closer to 5, you have minus 2, z to the power minus 1, right? Z into 5, you have 5 times z minus 2, you have that 5 here, and then you have, so continuing, sorry for that pause, we have, hold on, okay, so let's proceed one more time. So we have 5 times z to the power minus 2 times z to the power minus 2, z, and then we have 5 times 1.5, we have that 7.5, and then z to the power, it's z to the power minus 1 now, and then we have 5 times 0.5 is 2.5, and then we have z to the power minus 2, and then all of this gives us 5.5 z to the power minus 1 and minus 2.5 z to the power minus 2, and we continue now. Z into 5.5, we have 5.5 z to the power minus 3, and then we multiply that out, we get 5.5 z, we get minus 8.25 and then plus 2.75 minus 3, and then all of these we do a subtraction, we get a 0, we get a plus 8, sorry for that, this becomes not 8 but this becomes 5.75 z squared minus 2.75 z to the power minus 3, z to the power minus 2, not z squared here. And then we have z going to that, it goes into 5.75 z to the power minus 4. So we can go on and go on and go on and go on and so on and so forth. We'll just stop here. Now this means that the first few samples we have y0, it's going to be 2, y1, it's going to be 4, y2, it's going to be 5, y3, it's going to be 5.5, y4, it's going to be 5.75. So that's how it goes here. And for a moment you can see it's like it keeps on increasing as the output signal. So if it were to be out of the, if you were to have a sketch for it, it would be something like this. You know, something like that. So this would be your YKT as K increases. So yeah. So just make sure that you are able to do this long division. You always divide the first with the first one, and then you multiply that out to be the difference. So that's basically what you get with this method. Have you looked at how you assess your, or how you calculate the output of your sample data systems? We need to assess, generically speaking, what how you assess the stability of a sample data system. So generally speaking, stability of the sample data system can be assessed by plotting its poles and zeros on the z plane. On the z plane. So if you have, for instance, g of z being equal to z minus z0, z minus z1, and then maybe z1, and then you have z minus p1, and z minus p2, and z minus p3, and so on and so forth. So you can be able to plot. You can be able to plot here, say, can be able to plot your poles here. Let me not make that mistake. You can be able to plot, say, your poles here, P1, P2, P3, and then your zeros. You can be able to say plot a 0 here, 0, 1, Z0, Z1, and so on and so forth. Maybe you can plot Z0 here, and then Z1. So if you assess the plot on the Z plane, we will then say the stability of the transfer function here, g of z, is determined by the location of its poles. So the position of the poles on the z plane determines that. And the system is considered stable if all of the poles are within the unit cycle. So the unit cycle, this is the unit cycle. So if they are within a cycle of radius 1, if all of the poles, like in this instance, this would be a very stable system. If one of the poles sits on the margins, like maybe here, then it becomes marginally stable. So whereas in the Laplace transform, you had stability on the left half of the plane. In the z plane, you have stability on the just within the unit cycle. And here, obviously, you still have the imaginary. You plot the poles imaginary versus real. So anything that's within the unit cycle is stable. Anything that's outside the unit cycle is unstable. So whenever you have the poles inside, it's stable, outside, unstable, on the edge, marginally stable. Sorry, there. Let's take an example here, example 3. We want to assess, say, for example, is the transfer function g of z stable. So g of z in this case, this is my g of z. Now g of z, obviously because it's a second order system, we see that it has 2 poles. We see that it has 1, 0. And then we can foretell here, for example, the 0. The 0 means z is equal to minus 0, 1. So this would be the 0, for instance. And you can calculate where that 0 needs to be located. And then you can put it here. And because this becomes negative 0.72. So because you see these transfer functions normally on the Z plane, they are working on the very small spaces. And they have multiple points. They're a bit tricky to work with a calculator. You need a calculator to work with them. This one, for instance, you would need a quadratic formula to try and find out where the locations of these are. So in this case, for instance, your poles are going to be at minus b plus or minus the square root of b squared minus 4ac divided by 2a, whereby the b is equal to minus 1.368, the a is equal to 1, and then the c in this polynomial is 0.3679 according to this polynomial, and then you have to substitute that here and then use a calculator to do that. So it can be pretty much a tedious job, but an alternative to doing that is to just put these polynomials or the coefficients of the polynomials inside use your octave. You can just type roots for octave of this polynomial, and then it will give you the roots here. So this is approximately 1. Maybe let's take the first few, which we'll plot here. And then this is 0.36, which we'll plot here. So that gives you the poles. And so you can approximate your poles, you can approximate your zeros. Your 0 it can be approximated this way using that as well. So you can just type roots, looking the roots of that polynomial. And because here, with a fairly robust approximation, we see that the poles are, one of the poles is within, the other is right inside. So the system is, although marginally stable, the system is stable. The system can be said to be stable in this instance. So the idea for this is just to find the locations of the poles. In fact, the zeros are not very interesting when you're talking about stability rather than performance. But in this case, if you just find the poles, you find the location of poles, then you can say since they are within the unit cycle, they are within this unit cycle, both of these 2 poles, this one and that one. Then we say the system is stable, and we can use octave quite efficiently to find out quickly without needing to use this, the calculator to find out quickly what the roots of these equations are. And so, generally speaking, we can see like in the S-plane, we can do an analysis of what the location of the poles imply. What are the implications of the location of the pole on the performance of the system? So in this instance, for example, you see that if the pole is located here, which is like towards the right, next to the boundary, then the pole simply falls off. So you have an impulse response of a pole that dies off linearly like that. If it's outside towards the left, then it will just be bubbling out of proportion because it's unstable. Because it's unstable, the impulse response will just go out of order. It will just go up and up until it reaches and unbound and big values of infinity. And because of that, this happens because the system is unstable. This one happens because the system is stable. It's within the unit cycle. And then what's also interesting is that if you have two conjugate poles, but these two conjugate poles are also on the right side. If they're on the left, this doesn't happen. But if they're on the right side, then you will tend to have this oscillating response here. You have that nice oscillating response that damps off. But if they're outside, they're on the right, but whilst on the right, but they're outside the unit cycle, then they will tend to blow out into instability because this transfer function will be unstable. And then if you have them marginally stable, then you will hold on to like a sine wave or a cosine wave that doesn't die off. So it won't damp off because it's just on the boundary and it's marginally stable. And of course, like I'm saying, this will tend to happen. This will tend to happen for conjugate poles which are on this side. So if you have conjugate poles like this, you are not going to get this. You're not going to get this oscillatory behavior. You can test that using any transfer function in Octave. You will see. Octave. Try out that in Octave for any random transfer function. Just place those poles there. You will see you will have an output which is bounded, which is stable, but you won't have the damping like the one that you have here. Like the one that you have here. So basically this gives you an idea of the different locations, how they affect the performance of the so what basically how the different poles located in different positions on the Z plane behave, much like the analysis of the second order system in the S plane. And then you can see here the frequency of at which the oscillation occurs is related to this angle. It's related to the angle from the real axis. Yeah, so we'll not delve too much into that detail, but it's good for you to appreciate that. Now there are interesting properties to the Z transform. For instance, the Z transform has a linearity property. If you have a signal x of t and then you take k times x of t, the Z transform will simply be like the k times Z transform of the x of t itself. You can have a summation here, x1 of t and x2 of t. You sum them up, you look for the Z transform. The Z transform will be the same as summing up the Z transform of the individual signals. So in fact, if you look at these two, you will see that the Z transform also obeys the principle of superposition. If you remember what superposition is in unit 2. And then the Z transform at the delayed time t, it also depends on the initial value x of t, and then the Z transform of t times that, the ramp, it will be like a derivative. If multiplied by time, it will be a derivative with respect to z. And then you can do, for instance, your initial value theorem, and the Z transform will be z going to infinity for t is equal to 0. And then you can do your final value theorem to find the steady state error as well. X of t goes to infinity, so as t goes to infinity, in this case it would be like z going to 1 of the Z transform, but multiplying by z minus 1. So this you can use to find steady state errors for stable systems. By the way, it works for stable systems, and when all of these poles of x z of t are within the unit cycle. Let's take an example here of analysis of looking at the performance of a sample data system. So in this example, we will look at a simple example whereby we want to model the closed loop transfer function of a zero order Holt system, in this figure using our sampling time t is equal to 0.5 seconds. So t of s is equal to 0.5 seconds. And we will do that, and then we want to later plot the impulse response if this is an impulse. So remember, the impulse is just a signal like this. An impulse is just a signal here that goes to 1 initial when t is equal to 1. T is equal to 0, and then there's nothing for the rest of the time. So when you give it an impulse response, we want to see what should happen, what happens to y of t, and then we can also plot the step response here. So the step response would be simply, when you give it a 1 at the beginning, and it remains a 1. So you look at the unit step response as well. By step response, I just mean unit step response. The response is 1. So for that, remember we said you are going to model your system this way. You will load the package, the control system design toolbox. You will then create your transfer function, which is that. Remember, this is s squared plus s plus 0. So the coefficients 1, 1, 0. So this becomes the bottom coefficient of the numerator. And the denominator is simply 1. The top coefficient becomes 1. And then our sampling time, t of s 0.5, t of s 0.5. And so one way of doing that is then we model that transfer function. After modeling the transfer function here, we put in the sampling time of 0.5, and then we model it from continuous time to discrete time, GP of s, using this sampling time. And sometimes we can explicitly state that we are using the zero order hold. Although by default it will just do a zero order hold even if you don't put this as an argument, as initially shown. Because you can have different types of holds. You can have a first order hold, a second order hold, which we will not discuss and are beyond the scope of this module in particular. But you do that, so this gives you a g of z. So the g of z will be simply be the open loop transfer function. But what you are interested in is the closed loop transfer function. So your g of z will be in this form. So this is the open loop. Now we know that the closed loop, let's say t of z is equal to 1, is equal to g of z over 1 plus g of z. But you don't want to do that. So the simplest way of doing it in code is by simply writing this code here. So this code, by simply showing that there's a feedback loop connecting the 1, so unity feedback loop connecting to that, and then this should give you this transfer function t of z. So basically, you can also calculate it yourself manually using this, but you can do it in software clicker. This will give you that as well. So you can use this to verify your calculation as well. And so in this case, we have just managed to calculate, to model this, which is answered first question here. We have just managed to model this zero order hold system closed loop transfer function. So moving on to the second question, which is, now that we know the closed loop transfer function, which is this one, t of z. Now that we know the closed loop transfer function, which we call t of z, can we find now the step response? So in order for you to calculate the step response, you will, so this whole first block of code will be the one that generates this first answer. And then in order for you to plot the step response, you will take, for instance, your time. So you will say, give yourself step response. You will want to anticipate the step response for the first 20 seconds. For the first 20 seconds, and then remember our sampling time is 0.5, so we can use 0. So from 0 to 20 in steps of 0.5, This is the line that says that number 23, and then you say step t of z, which is the transfer function, t of t, which is the time, and then this should give you a response like this one. So this would be then your output y of t. So it comes in this nice and smooth format of an approximately analog continuous time signal. And you will see from the step response, you see there's a peak overshoot, there's a bit of damping here. In fact, you can tell that in this particular instance, you have a conjugate pole pair of zeros, of poles here in these poles must be a conjugate pole pair. You can find out, but you can tell by just looking at this graph how to do that there. And then now we want to answer the question which talks to, at this point we'll answer the question which talks to B. Remember we said for A, the first few answer A. So all of this, the answer number A. And then for the impulse response, which is this part, impulse response, when R of t is an impulse, you will do that. You set your time to 20 seconds, depending on what you want, and then you do your impulse response. You type in simply impulse t of z, and then it should give you this graph. But remember, by the way, you are able to do this calculation manually by simply taking your because your y of z is equal to t of z times your input r of z. So depending on, you use that table 13.1 to find what is the impulse response, what is the z transform of the impulse. You put that there, you multiply it together with this transfer function. After doing that, you get another fraction. That fraction you can use your long division assessment to find what your y0 is, your y1 is, your y2t, 1t, 0t, your y3t, and so on and so forth. You can find them out. Without using that here, we can tell, for instance, here, this becomes our y0, this becomes our y1, that is y2, that is y3. So we can zoom in on your picture after doing this result, but here you can clearly tell that your first sample y0 is equal to 0, your y1 is 1.01, your y2 it's going to be is y2, it's 2.5, 0.25, sorry, and then your y3, the first sample it's here, it's around 0.3, and then your y4 is here, so it's 0.204. So you can tell all of this by simply looking at that. So you can find your output if you are to calculate the first 4 samples or 5 samples or so. Now, one other important thing that you can do as an assessment is that you can actually look at the root locus analysis in the Z domain, which is very similar to the S domain. In fact, exactly the same. The only difference is that this time the chart you're going to plot is the Z domain. So the same rules apply of plotting the root locus. You can calculate the breakpoint the same way. You can calculate the angles of departures the same way. The same rules of that the root locus sits on the left of an odd number of poles and zeros, it applies. So, and then the major difference obviously is the stability region. So assuming you have something like this, you have a compensator here, which is your digital computer. So you have your digital computer in the loop, and then this digital computer is talking through a sampler and a zero order hold system to your plant, and then it's getting feedback, error feedback, which is in some point. So you can find the root locus here of what happens to the closed loop poles as k increases the parameter k changes. So you can have that, and this becomes your characteristic equation 1 plus k g of z d of z, and then so the same thing applies. Yeah. So for example, let's consider the example here where we are supposed to plot the root locus of the following system. So we have this open loop system k z plus 1. So you have a pole at 1, you have a pole at negative 1, a 0 at negative 1, you have a pole at plus 1, you have a pole at plus 0.2. Can you plot the root locus of what happens as k increases from 0 to infinity? What happens to these closed loop poles of the system? So closed loop poles are this. What will happen here? So let's look at that. So we can plot this root locus using the same code locus of k g d of z after creating k g of z, and then this will give us a picture similar to that. And then for instance here we can see that the root locus, so the root locus is here. This will be the root locus. So the poles start at the closed loop location of 1 and 2. So this would start there, and then they would move upward. One would move upwards that way, and then their second one would move downwards that way, and then this will go to infinity. The other one would actually go to the 0, which is the same way. So if you look at the location of the root locus on the real axis is here because it's on the left side of one pole. It's here. It's not here because it's 2 poles here. So it's on the left of 2 poles. So the root locus here is not there, but the root locus is here. And then on the left of the 3 of them, 1, 2, 3, it's also there. The root locus is there. And then you can see that because the second order system, the arcs are circular, much the same way as the root locus drawing method that we have used previously. And so we can calculate that. We can, for instance, here calculate here. The questions we find the values of k for each system is stable. So we can see here that the system is stable from this. Let me do that in green. The system is stable from this region to here, only up to here and here. So the moment the k starts exiting here, we see that the system no longer becomes stable. And we can find those values of k. First of all, we can know what this value is here, the values of the poles here, and then we can substitute this into 1 plus k g of z d of z is equal to 0. So we can find those values of z here. You can find the values of z at this point, and then substitute it into this equation, and then calculate what k is. You can find it that way. In this case, we see that at this point k is 0.8, so we can say from 0 k to 0.8. This has already been calculated, so this would be the range of k for which the closed loop poles are stable. And what is the value of the poles for the system is marginally stable? What is the point here? You can zoom in here. You can use your diagram to zoom in. What would be these values of z here? You can zoom in and find out from the diagram. Or, for instance, here, in this instance, you can do 1 plus k z plus 1 over z minus 1 and z minus 0.2 is equal to 0. And then you know this happens when at k is equal to 0.8. And then what you can do, you can say therefore This means that 1 plus 0.8 times z plus 1 over z minus 1 times z minus 0.2 is equal to 0. So you can have that here as your, you can substitute this value because you know this happens at 0.8 here. When k is equal to 0.8, that marginal stability. And substitute that into this equation, and then you will get an implication here. You can solve for z in particular for this equation, and then you will get that this means that z minus 1 times z minus 2, 0.2 plus 0.8 times z plus 1 is equal to 0. So can you solve this for, the value of z? Yes, you can. Which gives us, so this gives us, so if you take this, you take this and then let's finish it off here. You will have z squared minus 0.4 z and plus 1 is equal to 0. And then this, if you solve for this, you will see that your poles P0, P1 should be equal to 0.2 plus or minus J 0.98. So this post, the location of this post should be around there. And so we can find the value of poles when the system is marginally stable. Right. So at this point in time, we have familiarized ourselves with computer applications in digital control systems. We have looked at what sample data systems are, or why generally digital control systems are sample data systems. We have looked at what the Z transform is and typical examples of Z transform of common signals, the properties of the Z transform itself. We have looked at how to calculate the feedback transfer function of a closed loop sample data system, and we have seen how to use a computer and both manual, how you can do that. We have looked at the performance issues of these sample data systems, where the locations of, what the implications of the location of the poles on the Z plane mean towards the performance. And you've seen that you can even use the root locus to analyze the performance of these systems. So at this point in time, or at least after reading the tutorials, you should be able to understand the role of computers in the application of control systems design, and then you should be able to understand the Z transform and its properties. You should be able to analyze sample data systems using the Z transform. In particular, your long division, you should be able to do that, and you should be able to find the poles and zeros in particular, and you should be able to analyze the stability conditions of a transfer function of a sample data system. You can go on to read further sections of the book, 13.1, 0.2, 0.3, 0.4, 0.5, and 0.6, to grasp the concepts. The tutorial has also been given. Please do go through it, look at the typical questions that you might encounter and how to solve them. Most of these questions are also examples in the book. Go through them, look at the sample code, because your Octave toolbox is a very important tool in trying to solve these problems.